When you flip a switch, you just expect the light to turn on, right? But what if I told you there's something else happening inside those wires? Something invisible, a kind of electrical gunk that's silently stressing out our entire power grid. Today, we're going to dive deep into this hidden threat, known as harmonics, and our story actually starts in a pretty surprising place.
So let's set the scene. A quiet, rural area, the kind of place where you don't really expect major power issues. But one evening, seemingly out of nowhere, a utility transformer just gives up, fails completely, and the whole area goes dark. On the face of it, it just didn't add up. So what really happened?
Well, the investigation quickly zeroed in on the local golf course. Turns out they'd just wrapped up a big tournament and had dozens and dozens of electric golf carts all plugged in to recharge at the exact same time. First, a fuse in the clubhouse popped. Then, a little while later, the big transformer on the pole went out with a bang. This was more than a simple overload. Something much stranger was going on.
And that failed transformer? It's really just a symptom of a much, much bigger problem. Our modern electrical grid is being pushed to its limits in ways it was never, ever designed for. And the cause is hidden in the very shape of the electricity we use every single day.
And that culprit has a name: electrical harmonics. The best way to think about it is as noise or pollution on the power line. It's generated by all the gadgets that define our modern lives, and it was the real, hidden reason that transformer just burned itself out.
Okay, so take a look at this. On the left, you've got this beautiful, smooth sine wave. That's the dream, right? That's the clean, predictable power our grid was built for decades ago. But on the right, well, that's the messy reality we live in now. See how jagged and ugly that is? That's a wave that's been polluted by what we call nonlinear loads. Instead of sipping power smoothly, these modern gadgets take big, sharp gulps, and that's what creates all this electrical noise. So where is this distortion coming from? Well, pretty much everywhere. The power supplies in our computers and TVs, the drivers for our LED lights, those EV chargers, and the variable speed drives in everything from air conditioners to big industrial pumps. Basically, if it's a piece of modern electronics, it's probably creating harmonics. Now, you can't fix what you can't measure. So, how do engineers actually quantify this invisible pollution? Well, they've got a very specific metric that puts a hard number on just how messed up our power has become.
And that metric is called total harmonic distortion, or THD. It's just a percentage that tells us exactly how much a waveform deviates from that perfect, clean sine wave. A pure sine wave would have 0% THD, so the higher the percentage, the dirtier the power.
And how high can that number get? You're not going to believe this. In a real-world test of a variable speed drive running at a pretty light load, the current distortion, its THD, hit an incredible 77%. Now, the actual amount of current was low, but it just goes to show how wild the distortion can get. And that brings up a really crucial point. We have to separate the cause from the effect. The cause is current distortion, or THDI. That's our devices drawing power in those weird, choppy pulses. As all that messy current flows through the grid's wires, it creates a distorted voltage drop. And that gives us the effect, voltage distortion, or THDV. And that's the problem that everyone connected to that circuit ends up feeling.
Okay, so now we know what harmonics are and how we measure them, but why should we care? What's the big deal? Well, this electrical pollution has some very serious, very physical, and very expensive consequences for our infrastructure.
See, this pollution doesn't just vanish. It turns into wasted energy, and that wasted energy shows up as heat. This rogue heat literally cooks transformers from the inside out. It bakes the insulation on cables until they fail. It causes circuit breakers to trip for no apparent reason. It's like a ghost in the machine that makes sensitive electronics go haywire and causes critical, expensive equipment to fail way before it should.
But here's the thing, not all harmonics are created equal. There's a particular group that is especially nasty, especially in the three-phase power systems that run most of our commercial buildings. They're called triplins. That's the 3rd, 9th, 15th harmonic, and so on. And these guys have a very dangerous habit of ganging up where you'd least expect it.
So here's where it gets really scary. Normally, in a big three-phase system, the currents on the three main wires are supposed to cancel each other out. This means the neutral wire just kind of hangs out, carrying almost no current at all. But triplins, they don't play by those rules. They don't cancel. They do the exact opposite. They're all in sync, so they gang up and add together on that poor, unsuspecting neutral wire. And suddenly, a wire designed for almost zero current is carrying a massive load, turning it into a red-hot heating element. And yeah, that is a massive fire risk.
So this is clearly a huge global problem. And because it's so serious, a whole framework of rules and standards has been developed all around the world to try and keep this electrical pollution under control.
In North America, the big one is IEEE 519. Internationally, you've got the IEC 61000 series, which serves as a foundation for countries everywhere. You see it adopted as AS/NZS 61000 down in Australia and New Zealand, or as the ENA G5 recommendation in the UK. The physics is the same everywhere, of course, but each standard is tweaked for the local grid. The goal, though, is always the same: limit harmonic distortion.
Now, to enforce these limits, you need a line in the sand, a place to take your measurements, and that place is called the Point of Common Coupling, or PCC. It's the official boundary where the utilities grid meets a customer's building. It's where the power company can say, okay, right here, at this point, your electrical pollution cannot go over these limits, period.
And this table gives you a pretty good idea of what those limits look like. This is from the IEEE 519 standard. You can see there are strict limits on voltage distortion, usually around 5% for most of us. And the limits on current distortion, which they call TDD, can vary a bit, but the message is crystal clear. There are firm boundaries you are not allowed to cross.
And here's the cover of the UK's rulebook G5. I mean, documents like this are incredibly detailed. They lay out these complex, multi-stage processes for how to safely connect new equipment to the grid without causing problems. It just shows you how seriously engineers and utilities take this threat.
So, the problem is clear, and the rules are in place. But how do we actually fix it? This isn't just about setting limits. It's about actively engineering ways to clean up our power.
The good news is, engineers have a whole toolkit to fight back against harmonics. It can be as simple as smart design choices or specifying equipment that's built from the start to create less distortion. But the real heavy hitters are filters. Passive filters are like a strainer. They just block the bad harmonic frequencies. Active filters are way more high-tech. They actually monitor the distortion and inject an equal and opposite current to cancel it out in real time.
And this is the proof in the pudding. This is a real report from a hospital. On the left, it's just a sea of red fail marks. I mean, they were completely out of compliance, way over the limits. But then, look at the right. After engineers went in and installed the right harmonic filters, bam, all green, all pass. It's such a perfect example that yes, this is a huge problem, but it's a solvable one.
Which brings us to our final big question. We've seen that harmonics are basically a side effect of the modern, efficient electronic world we're all building. But as we keep adding millions of EVs, smart devices, and all sorts of new tech, the level of this electrical pollution is only going to go up. We have the tools to manage it for sure, but it leaves us with a critical thought. Is the fundamental design of our grid, a system built for a simple world of incandescent light bulbs, truly ready for the distorted, electronic future it will be forced to power?